I'm going to pass around the roster. So if you are officially registered, make sure you sign the roster. Otherwise, you don't get credit for today, okay? So please make sure you sign the roster. Okay. Apart from that, I think we can get started. We have a special guest here today with us, and I'll have Professor Mon Hubbard introduce him.
Thank you. Today we're very honored to have Professor Manoj Srinivasan, who's a professor at Ohio State University in mechanical engineering. He got his undergraduate degree at the Indian Institute of Technology in Madras, and then did his graduate work in the Department of Theoretical and Applied Mechanics at Cornell. After that, he did a postdoc at Princeton before he started his present position. And he works on biomechanics generally, mechanics of locomotion somewhat, and optimization. So today he's going to talk to us about a particular aspect of that.
Thanks, Mark. Can everyone hear me? Okay, perfect. Thanks for inviting me. It's been wonderful so far, and I'm going to be here for a couple of more days. So if people want to meet me, I would absolutely like to meet you as well. And I hope to have more interesting conversations over the next couple of days. So I have 3 presentations open, and a couple of them are pretty short, maybe 5-10 minutes long, and then one of them is somewhat longer. What I'll do is start with the short one and then do a long one, and then if you have time again, we'll do the short one. Okay. Most of this talk, as Mont pointed out, will be about how people walk and run. So something about how people move, human locomotion. Okay. This short 10-minute talk is all the experiments were done by Leroy, who was a master's student at OSU with me recently. Okay, so let's start off with the basics. That's just a couple of videos of a person walking and a person running normally on a treadmill. Of course, when humans want to move from point A to point B, they either walk or they run, more or less. And they walk when they are not in a hurry, that is, when they want to walk only at low speeds. And they run when they want to move at higher speeds, right, when they are in a hurry. So this sort of phenomenon of going from walking to running is called gait transition. Just to introduce the word, the word gait means one of the common patterns of movement that people use. Say walking is called a gait, running is a gait, and so on and so forth. One classic experiment that people do is actually is something that perhaps all of you are familiar with if you've been in a gym and run on a treadmill. As you slowly increase the speed of the treadmill, you're probably initially walking, and at about some speed, maybe around 2 meters per second, you start running. Right? You start breaking into a run, and then if you decrease the speed again of the treadmill, you would start walking again. Right? And this phenomenon of going from walking to running or running to walking is called gait transition, transition from walking to running or running to walking. So this treadmill gait transition experiment can be done not only for horses but also for not only for humans but also for horses. And this is an experiment in which they actually did it on horses. There's a treadmill, it's a big horse treadmill, and what you will see is the treadmill speed increasing very slowly, and then you will notice that the horse goes from one gait to another. Okay, so the treadmill is going slowly, and then increasing the speed of the treadmill breaks into what looks like a run, but it's called trotting. where diagonally opposite pairs of legs strike the ground simultaneously. It's as if you replace one leg of a human with two legs of the horse. So, and then as you increase the speed even more, it breaks into something that people call galloping. Right. So just like people have at least two qualitatively different gaits, walking and running, horses have three at least. Some horses can do more gaits, but we won't talk about them. And you might ask, hey, why do people and horses have these different gaits? And why do people and horses go from one gait to another when they want to go faster, right? Just to back up a little bit, you might say that's a silly question. The only way maybe you can go fast is run. But that's not clearly true. That's clearly not true because in principle, you can just walk very, very fast, right? So when you want to go fast, you have a choice of either just walking very, very fast or running, where running is defined as a pattern of movement in which both feet are off the ground simultaneously at some point during say. So that's how you define running. Walking is, at least I would define as a gait where both feet are on the ground some of the time, and then at least one foot is on the ground all the time. Okay. So in principle, you could just do this, which is walk very, very fast without lifting both your feet off the ground at any point in time. But you just don't do that. And you might ask why. And the answer to that question, at least some of us think, lies in pictures like this. This picture is running speed or walking speed on the x-axis, energy on the y-axis. This is actually energy per unit distance on the y-axis. And the way you measure energy per unit distance, or energy indeed when a person or an animal is walking or running or doing whatever, is by measuring the amount of oxygen and carbon dioxide inspired or expired through the nose or the mouth or so on. And that gives you at least an approximate estimate of the amount of ATP that is consumed by the person, which is the currency for energy that every muscle uses. And essentially by measuring, by putting a big mask on this arse and measuring the amount of oxygen, carbon dioxide exchanged, you can measure the energy per unit time. And that's what they did to actually create these plots. So to create these plots, what they did was put the horse on a treadmill, make it walk here at 1 meter per second for a while, measured the energy cost, and then computed energy per unit distance traveled, right? So every point on that is an experiment like that, and then they increase the speed to an extent that the horse wants to trot. Actually, they trained the horse to trot at a bunch of different speeds, and then got this curve, and then they trained the horse to gallop at a bunch of different speeds on a treadmill again, and got these curves. Okay. And you notice, first of all, about these curves is that these curves cross somewhere, and they cross here, and which means that this is the walking cost, this is the trotting cost, this is the galloping cost, and this crossing means that beyond the speed, walking is more expensive than trotting, and beyond the speed, trotting is more expensive than galloping, and beyond the speed this way, walking is less expensive than trotting. So it would make sense if the horse were to prefer to walk below the speed and then trot above the speed, and so on and so forth, right? So this is an energetic explanation for why animals, and humans in particular, change from one mode of locomotion to another. The explanation being that if you do something else, if you walk here, you would just be wasting energy, so you trot, right? So that's a classic explanation. There is some controversial aspects of it. Apparently, the speed at which horses transition from trotting to galloping is perhaps substantially different from this point. Right. So there's at least some people found that, and other people found that it's actually pretty close to this. So there's some experimental controversy dating back to at least 10, 15 years. But at least this is one classic theory for why animals transition from one gait to another. Humans looks like this. This is on the previous slide. I had energy per unit distance. This is energy per unit time. But at least for the purposes of this gait transition business, this crossing is still the same concept. You would expect, at least superficially, that if walking is more expensive than running beyond the speed, you would expect people to start running instead of walking beyond a particular speed. This speed is around 2 meters per second. So this is energy per unit time. Energy per unit distance actually is obtained by taking the previous slide, the curves on this slide, and then dividing the curve by velocity. You get energy per unit distance. And typically these curves have minima, like so. The running energy cost, again, there is some controversy as to whether or not there is an actual minimum or whether it's pretty flat. But walking definitely has a very clear minimum, and this minimum happens to be roughly at a speed of 1.3 meters per second. It differs for different people and so on. But what does this mean? So it means energy per unit distance is minimized at about 1.3 meters per second. And it turns out that if you just go to a big railway station, airport, or just watch people on the streets and measure the speeds at which people walk, you will find that people walk at a variety of different speeds, of course. Some people are in a hurry, so they're walking fast. Some people are just milling around, they're bored. But a lot of people will be walking at actually pretty close to the speed. There'll be a broad distribution starting from here, like so. So I'm just sort of plotting, if you will, the histogram of speeds at which people walk outside on the streets. And this histogram, it turns out, if you actually measure it, has a peak somewhere around here, okay? Which suggests that people prefer to walk while close to a speed at which you minimize the energy per unit distance traveled. It's not exact, the matching of the peak. It's all pretty approximate, but at least it's approximately true that energy per unit distance is minimized. At least people are not wildly inefficient in terms of energy per unit distance. Just to back up very slightly, this horse slide that I had these black block-looking things. And what are those things? I didn't really talk about those. So these guys, Hart and Taylor, which is a classic paper in Nature 30 years ago now, so they came up with these curves for explaining gait transition. And then what they did was let the horses walk / trot / gallop around in a pleasant meadow for a while, and then videotaped them for a few days, I think, and then noted down the speeds at which, so there are no constraints now, no treadmill, no nothing, they're just doing whatever they want to do, and then they just noted down the speeds at which they walked when they did walk, speeds at which they trotted when they did trot, and so on, right? And these are the histograms for those things. And when they did walk, it turns out that they did not use too slow speeds. They did not use speeds out here. Rather, they used a relatively narrow range of speeds here, which roughly lines up with the minimum here. And similarly for trotting. And galloping, of course, I think they did it so rarely, naturally, that it's not clear if that's too interesting. So that is sort of analogous to human situation, where the speeds at which people prefer to walk lines up with the minimum of energy per unit distance traveled, approximately. Any questions so far?
Why is it that if you walk so slowly, it consumes such big amounts?
Aha. Okay. Good question. So this is energy per unit distance. Okay.
Maybe you could repeat the question
Okay.
for our remote.
Will do. So the question was, why is walking slowly costing so much, right? So it actually not only does it cost a lot, it actually costs infinity mathematically. And the reason is the following: if you're just standing still, it costs you something, right? The energy per unit time when you're standing still is some quantity, which is actually is on the previous slide. So walking metabolic rate, I just wrote down some formula, which is a fit to experimental data. It's 2.2 watts per kilogram if you're just actually walking very, very, very slowly or something like that. If you're just sitting down right now as you are, I think it's about 1 or 1.4 watts per kilogram. So if you're sitting around and if you weigh about 60 kilograms, you're consuming about 100 watts of energy. So maybe less than that bulb. I don't know how much that bulb was consuming, but so it's a pretty small amount. But it's a non-zero quantity, right? Which means that when you actually walk very, very slowly, arbitrarily slowly, to get anywhere, you will take infinite time, which means that when you get there, you will have consumed infinite energy, right? So energy per unit distance, because of this resting cost, is infinity.
That actually brings out another question.
Uh-huh.
That if you just stand there still, the energy consumed is for your metabolism.
Yes.
Would that be fair to include that energy into walking and running? I think it should be excluded.
So that's an interesting question as well. And there are arguments for both including and excluding, valid arguments. So you might say, hey, why do we care about energy per unit distance? And what energy should it be per unit distance? Should it be total energy, including all the metabolism, or net energy, which is total energy minus the resting cost? And why should we consider energy per unit distance at all, right? Why should it be the right thing to minimize, you might ask? It's kind of the right thing on an evolutionary time scale, you might say. If food is scarce and you have a given stomach full of food and you're trying to look for food, minimizing the total energy per unit distance, not the net energy per unit distance, is the quantity that maximizes your distance traveled for a given stomach full of energy. It is the speed at which you want to walk or drive your car if you want to maximize your mileage, right? So subtracting metabolism is like subtracting, say, idling or something like that. So if you want to maximize the probability of finding the next gas station with a given amount of fuel in your gas, then you want to just minimize the total energy rate. Okay, so moving right along. There's a bunch of different pieces of evidence for this energy optimality. We actually, the first few experiments were done by Ralston, where he actually asked people to walk very naturally, and then they found that the speed at which people walk naturally roughly corresponds to the minimum of this cost. And then, more surprisingly, he made people, amputees, walking with crutches or prosthesis, and found the energy cost per unit distance for them. And he found, of course, that the energy cost per unit distance for them were higher because they just consume more energy per unit at a given speed. but they were also shifted to the left a little bit. And when he asked him to walk naturally, he found that the speed at which they preferred to walk lined up roughly with the minima of these curves as well. And you might argue, as he argued, that the reason why an amputee perhaps walks slower than normal humans do is not just because his or her speed might be constrained by the disability, but because the lower speed is actually the thing that minimizes the energy cost per unit distance. It's a slightly different hypothesis. Okay, so that's all well and good. And as I mentioned, the classic gait transition experiment is done on a treadmill, right? So you slowly increase the treadmill speed to see transition from walking to running or running to walking. But I just want to consider a slightly more realistic gait transition experiment. And this is the experiment that we did, right? So the usual gait transition experiment is done on a treadmill. And as you all know, a treadmill constrains speed, right? A treadmill is relatively short. It has relatively short length, so you cannot move forward or back all that much. So if the treadmill has a speed, you're pretty much stuck at that speed. And the choice, in the classic experiment, the choice is between walking or running, right? So typically they ask the subject, do whatever is natural, but pick walking or running. And that's how they see that walking is preferred at slow speeds and running at high speeds and so on, and then a reasonable gait transition speed in between. A different experiment you might do is not on a treadmill. I don't know if I would call this the most natural experiment, but it is maybe a more natural experiment for normal people walking around, say on this campus, rather than the treadmill experiment, right? And the experiment is to go from one place to another, and maybe the talk you want to go to starts in 5 minutes. So there is a time constraint, right? So distance is specified, you know, the starting and end point, and then the time duration is specified, but the velocity at any point in time is not specified, right? So it's a slightly different proposition. And so we actually did this experiment, and we just wanted to see what people would do. You might already guess what people might do, but we just to measure various things, we put a bunch of equipment on it, like GPS devices and so on, to measure the speed at which people travel. Let me just skip over those things. Right. So what would you expect people to do? Of course, if let's say in our experiment, actually, the distance that we prescribed was about 120 meters, just something that we picked. We also picked a few larger and smaller distances, but the most common distance was 120 meters. But let's say it's something, the total distance is specified, and then let's say the time that you have is 20 hours, some huge amount. What would you do, right? And the natural answer would be you would walk from A to B at some speed. Let's say the time that you have is only a few seconds, maybe 30 seconds, right? For about 120 meters, 30 seconds would imply you essentially have to run as fast as possible, right? So if you want to go from A to B and you have time to kill, of course you would just walk slowly. And if you want to go from A to B, and if you don't have all that much time, very little time in fact, you would just run at some speed. That's what you would expect. And perhaps if there is an intermediate amount of time, maybe your inclination would be to walk for a while because it's more comfortable. And then maybe you find that time is running out. Maybe you run for a while, and then walk for a while, and then run for a while. So that you probably sort of feel that would happen if sort of an intermediate amount of time you probably experience this in your life, and that it turns out this is actually a collection of a lot of subjects, so data looks a little bit messy. But let me don't focus on too many things. Let me just unpack this picture for you a bit. So the x-axis is the average velocity that you essentially prescribe, right? So the total distance is prescribed, the total time is prescribed. So we are prescribing the average velocity, which is total distance by total time. If the average velocity, and so that's the x-axis, the y-axis is the fraction of running or walking. Okay, the red points is the fraction of running, and what a single red point means is the following: if you are asked to walk at an average velocity of 1 meter per second, which means for 120 meters you have 120 seconds to cover it, then the person would just walk all the way. Right? So all these red points say that if the average velocity required of you is pretty low, you would just walk 100% of the time. Right? So this is a fraction of walking during the whole period. And these people are walking essentially 100% of the time. And if the speed is very high, of course you would run most of the time, so you would walk very little of the time. And it looks like what people are doing is actually close to mostly running. It looks like about 80% running, 20% walking, at least. And then there is an intermediate range where you do a mixture of walking and running. Yes?
Is that the fraction based on distance or time?
This is a fraction based on time. Yeah. Other questions? Okay, so now I sort of motivated this result, expecting this result by saying something like, in this intermediate time range, you might just sort of feel like you want to walk and then feel like you're running out of time, so run and so on. But it turns out that this is exactly what is predicted by energy optimization as well, as we'll see in a moment. This is actually just a plot of one of these intermediate speed trials where I think it looks like the total number of seconds that was required is 60. The person walked for a while and then ran for a while. The thing is noisy because it's this is velocity, by the way. So it's walking at slow speeds, and then the person transitions and runs for a while and then decelerates to essentially zero. Let me skip over that. So what does the theory say? It turns out that you can actually predict that there should be a mixture of walking and running in between this walking only and running only regimes. So this is actually energy per unit time, and you can show using some relatively simple math that the speed up to which you have to walk all the time is actually when you actually draw a tangent from tangent between these two curves, right? So this is the walking cost, this is the running cost, and the basic idea is that the lower convex envelope, if you will, of this curve is let me say that again. The lower envelope of this curve is non-convex, which actually has the following implication. It means that by doing a mixture of walking and running, you can actually do better than doing either walking or running. Let me say that slightly differently. So if you're at this average velocity, the best thing you can do is just walk. If you're at this average velocity, the best thing you can do is just run. If you're at this average velocity, if you walk, you will be somewhere on this blue curve in terms of energy consumption. You will be somewhere here if you just run. But what you can do is walk at this speed and run at this speed and sort of switch between the two, and you will find that you reduce the total cost from either of these two curves to the starting line. Right. So it turns out that you can actually do something better than just either walk or run in this intermediate regime, which is better than walking and running, and this is actually predicted by energy optimization. I guess at this limit you would do all walking, at this limit you would do all running, and this is a gradual change from all walking to all running. And this theory is actually pretty, it's in some obscure paper from 1986, never cited actually. And this theory is related is a number of, is similar to that observed in a number of different fields, including material science, where you find something called twinning microstructure, in which you have two kinds of materials intertwined that minimizes the energy more than just one kind of material and things like that. Okay, so theoretical prediction looks like that. Forget this curve. As you increase the average speed, all walking is here, all running is here, and then a mixture of walking and running is predicted. Okay, so at least approximately, it looks like even in this slightly more realistic setting, energy optimization predicts what people do. You might have a number of questions, things like, well, actually, energy optimization doesn't really, at least in the simple context, doesn't really predict how many switches people should do between walking and running. If there is a cost to the switch, then it turns out you just have to do exactly one switch. If there is no cost to the switch, you can do as many as you want, and it doesn't matter. It doesn't predict any dependence on the distance, but we haven't really figured out if people actually have a dependence on the distance. And it looks like if people practice this over and over again, still the qualitative phenomenon is definitely present, it looks like. With this theory, you might actually make other predictions. So we said treadmill locomotion is speed constrained, but if you had a long enough treadmill, then you're no longer speed constrained. There is a long treadmill, you can run forward and then slowly coast back, potentially, and then run forward, slowly coast back, and so on and so forth. So in principle, for a long enough treadmill, you're not speed constrained. And if you had a long enough treadmill, and if you're in this range, we would predict that you should do a mixture of walking and running. You should probably run forward a little bit and then maybe walk a little bit back and then run forward and so on. Maybe the theory also applies to children walking with parents, right? If you notice, I guess, some children, when they're walking with their parents, are lagging behind for a while, and then running up to catch the parent, and then lagging behind for a while, running up to catch the parent, and so on. It might be that behavior is just something behavioral, something sort of idiosyncratic, children not explained by biomechanics, but maybe that is actually the thing that minimizes energy consumption as well, right? So it turns out, or at least there is some evidence that if you have a parent, a bigger person, that has this curve, these two curves like so, and the parent is walking at some speed, right? So the parent is walking perhaps at his or her optimal walking speed, somewhere out here where walking is optimal, maybe. And the child needs to, on average at least, tag along with the parent, but there is some leeway in terms of how closely the child follows the parent. And the child's curve are shifted to the left because the child is smaller. So which means that the walker and mixture regime of the child actually falls in the normal walking speed regime of a larger person, which means that you might expect this intermediate locomotion for children when they are walking alongside a parent. Right? I think there is some circumstantial evidence, unpublished, I've heard, that there are some animals where juveniles, again, walking with adults, that exhibit this behavior, where the adults are walking or doing something at a constant speed, and then the juveniles are maybe crawling and then flying and then crawling and flying or something like that. And then this is too speculative. If you walked a dog, I guess they also lag behind sometimes, but it's not clear if they might just be interested in something interesting smelling. But many of these things you can actually test experimentally, I guess. So that was just the first piece of my talk, which was a small experiment, a small extension, if you will, of classic experiments, where we took the classic gait transition experiment on a treadmill, put it on the ground, and then gave people, instead of speed constraint at every point in time, we just had a average speed constraint over a period of time, that is total distance and total time, and then observed what people did, and then what people did, which is a mixture of walking and running at a range of intermediate speeds, is at least roughly predicted by qualitatively energy optimization. Okay. So that's just a small project, but I would say the overall goal of our research program is what we would call a predictive theory of human locomotion. Right? We would like to understand why people and animals walk and run and do the other things the way they do, and if you actually had a theory like that, what are the kind of things that we might understand? How am I doing on time? 10 minutes? Okay. Okay, so maybe I'll go a little bit faster on this. So this is called the Millennium Bridge. It was built about 10-15 years ago, and they opened it in commemoration of the millennium, the year 2000 in London. And when people got on it, turns out that it shook from side to side, and they didn't anticipate it. This is an example of human walking interacting with external structures. Even though a bunch of people have written papers explaining this from a mechanics perspective, I think the human response to things like that is not completely understood. Of course, you might know this person, Oscar Pistorius, who runs essentially as fast as a human with prosthetic legs, and various people have various questions of the kind. Can we design a prosthetic leg that outperforms the real leg? If you have a prosthetic leg, can we predict the performance, in this case running speed, of a person wearing it, and so on? Right. So I would say we don't have theories in place to be able to predict things like that yet. And this is a classic video from 30 years ago in which you see an astronaut bunny hopping on the moon, and you might ask, why do astronauts, at least most commonly, if not all the time, use this kind of locomotion on the moon as opposed to walking or running? People believe, and some people have done some calculations which suggest this is the case, that it's energetics again. But I wouldn't say the case is closed that people move this way on lunar gravity because it's energetics. Maybe about a couple of years ago, when I asked this question, why do astronauts bunny hop on the moon? In a seminar, someone from the audience piped up, and said, hey, maybe it's just because they're on the moon. You're just so happy just skipping around. So that's a plausible theory. Anyway, I would say overall we don't understand legal locomotion well enough to answer these questions with great confidence, and in particular good enough quantitative detail before doing the experiment, right? So, and that's kind of one of our goals. And this is a slide I suppose I showed you earlier in a different form. Over the last 50 or 100 years, people have characterized walking and running various different ways. Walking as something called an inverted pendulum gait, running as something called a spring-loaded inverted pendulum gait, in which the leg is relatively straight in walking, and then the leg walls over. There's the toe off, there's the heel strike. The toe off is when your rear foot pushes off, and then heel strike is when your front foot hits the ground, and so on. And then running, people at least approximately characterize as flying through the air, bouncing on your leg like a spring, and then flying through the air, bouncing again like a spring on the ground, and so on. So these characterizations go back at least 50 or 100 years. Some of these characterizations go back 200 years, I think. So it's very old. And you might ask, very generally, is that all our legs capable of? Right? So why do people walk and run like that, the way these characterizations are, if you will? The answer to this question is that all our legs capable of is definitely no. Human legs have, each human leg has at least 50 muscles controlled by the brain, and human legs can not just walk or run, but is capable of all kinds of strange and silly gaits. Have people seen this before? Okay. So he's a professor, or at least was a professor some time ago at Cornell. He was given an honorary professorship at Cornell. So the scientific question is, why do people walk and run as opposed to moving in a million different ways, other ways that they are capable of, right? And the answer to that question, again, a possibility, it's a hypothesis, is that animals minimize energy. That is, they minimize, they try to walk in a manner that makes them least tired, right? And this hypothesis, as a hypothesis, again, is very old. Okay. So earlier in the first part of the talk, I showed examples of energy optimality for speed in particular. But here we are not just talking about speed, but actually the way in which each of our segments move. So to actually be able to predict how each of our segments move as a function of time, you want a stronger hypothesis. Not only that the speed that we walk at is roughly optimal, we would like to hypothesize that the way in which every segment of our body moves when we walk is at least approximately optimal in terms of energy. That is, walking as we do is better than absolutely everything else that we can think of at low speeds, and running is better than absolutely everything else that we can think of at higher speeds. Now, how do we test this hypothesis? Well, we can do an infinity of experiments making people walk in all the crazy ways that guy did, and then see what the energy cost is, and then compare it with a normal human walking and running and show that it's higher. That's one way to go. And perhaps you can do some of those experiments, and people have done those experiments, some of those experiments, but maybe a better way, a more useful way eventually would be to make a model that can actually, a mathematical model that is capable of all the crazy walks and runs, and a model simple enough that we can actually find out what the best way for it to walk and run are, right? So that's what we're going to do very quickly. So the model that we considered looked something like this. Maybe you can ignore this picture. They're actually completely equivalent. It had a point mass body, maybe a leg with one segment, one muscle. The legs are essentially massless, and the body, all the body is concentrated at the hip. So it's a really ridiculously simple model. So those are just assumptions of the model. And the equations of motion for this model are no more complicated than what you learned in high school, perhaps, maybe freshman physics. So when one leg is on the ground, the forces on it are mg and the leg force. The leg force is something that you can pick as a function of time. And by picking that, you can move the body around various different ways. And these are the equations of motion, right? So. And this model is, in fact, capable of a lot of crazy things. In fact, you can draw a wiggly line on the board, and by appropriately changing the leg length as a function of time, or the leg force as a function of time, you can make the model track. Well, not essentially every wiggly line on the screen, but a relatively large class of wiggly lines on the screen. So it's capable of a lot of things, a lot of crazy things. In particular, all kinds of crazy forward-moving hip motions of the person. And then we have to say. When we say we want to minimize energy, we have to define what energy is. This is the simplest cost that we picked. Linear combination of positive and negative mechanical work, but turns out for this problem we can actually pick, this is reasonably realistic but not completely realistic. You can pick more and more complex models, and it turns out the results that we get are almost exactly the same qualitatively, almost exactly the same quantitatively for more complex and realistic models that we pick. So you shouldn't pay too much attention to this cost model. So once you take that model, and then once you have this cost that you want to minimize, you might ask what the best way to minimize this are. We go through what would be a numerical optimization problem where we try to find the leg forces as a function of time, which would translate to leg length changes as a function of time and position changes as a function of time, eventually initial conditions, and a bunch of other unknowns. So the motion of the body is unknown. And then we want to say what should the motion of the body be so that we minimize the cost subject to a number of constraints. The constraints being that the thing is periodic, right? Step after step, the motion is the same except translated forward. And then you have to walk and run, or walk or run at a particular speed and stride length. And then we check what the optimal strategy at various speeds and stride lengths are. Let me just numerical methods here. So how should the model biped move? It turns out that we found 3 distinct optimal gaits depending on speed and step length: walking, running, and something else. And this is what you might call a phase diagram, where x-axis is speed, y-axis is step length, and for low speeds and low step lengths, we found this thing that looked like walking, it turns out. We call inverted walking. And then for high speeds, we found something that looked like running, and then intermediate speeds, something intermediate. So the optimal walking gait, it turns out, is actually, this is not the greatest animation, but what happens is the leg is exactly straight in the simple model. It walks over in a circular arc, and then the next foot hits the ground, and then it goes on a circular arc here, and then so on, right? So it looks like that, essentially, where the leg is, well, exactly straight, and this is discovered by the optimization, and it is a motion that was posited as a simple model of human locomotion, like I said, 50 or 100 years ago. Right? So it's interesting that this optimization discovered this naturally without our asking it to move this way. Right? Among all the different possibilities of walking at this low speed, this was found to be optimal. And then running is actually flying through the air, bouncing, and depending on what you put as the maximum force, the bounce can be somewhat compliant or very stiff and so on. I think the animation shows a particularly stiff bouncing gait, but that's just what I picked. And then the pendular down, maybe I'll skip over. But this is the gait that we found to be intermediate between walking and running, which has some properties of walking and running, which is predicted by the model, but it's not clear if it's actually seen in nature. So that's really simple model predicted some things like that to walk slow you have to walk, to go slow you have to walk, to go fast you have to run. But what we would really like is a model that predicts lots and lots of different things, like preferred speed, step length, how much your feet is on the ground, what your muscles are doing at any point in time, energy consumed, all those things we would like to know at all kinds of different situations: level ground, uphill, downhill, altered gravity, uneven terrain. So given a condition and given a person, we would like to be able to predict how this person will move. That simple calculation I showed is just a simple calculation, maybe far too simple, but what we would like to do is actually build on those simple calculations slowly, and we are making progress on these calculations. Some people are already doing more complex calculations with more complex models, but we are building up slowly, so that's the calculation that I showed, and then you can actually have more and more complex models. Let me actually show, for instance, what is possible with a complex model. This is not quite minimizing the right quantity, so the upper body looks a little bit weird. But this is an example of how a person would move. So this is an optimization with a more complex model than I just showed, but this is a calculation in which I artificially increase the leg length. So this was like the base leg length. This was twice the leg length, 3 times the leg length, and half the leg length or something. So you might, in principle, be able to run these optimizations to make predictions about how people with different leg lengths, for instance, might walk, or you can imagine all kinds of different variations. Of course, you could do this experiment in principle where you add to the leg length of a person by adding stilts or something like that. Maybe you cannot do this experiment where you reduce the size of a person's leg. But I guess the reason why I showed this animation is to indicate that you can ask a number of hypothetical questions using this methodology. But where are we going with this line of research is the following, right? So I had this big wish list of things that you would like to predict, and we can do experiments under all those circumstances. And what we would like is to have some ability to do what I call forward optimization, to be able to test the theory under all those circumstances and be able to actually predict how people walk and run under all those circumstances. I guess we've sort of run out of time. Maybe I'll stop there and then address questions if people are...
Maybe one question and then we should wrap up. Yeah.
I have 2 questions.
Pick one.
I have a question about evolution. You said the modern biped is actually supposed to walk in a certain way for energy optimization, but there were times when we used to walk on all 4 limbs, right? So, I mean, at that point, the human body would have been like in a different physical disposition. Maybe at that point, it was better for the human body to move in that gait.
Absolutely. Right.
So do you think that I also read about the gait of the human body, the walking stance, that can change with time, like not a lot. Do you think that it's going to change in the future?
Okay, maybe I'll answer the first question first. So I think maybe it was maybe more of a comment.
I think my broader question would be how would evolution fit
into this paradigm, right? So I think the narrow hypothesis we are making is that a really broad hypothesis one can make is that, which maybe is too strong, is that both the structure of the human body and its function is optimized for its evolutionary niche, if you will, right? But maybe that's too strong. You might make a more narrow hypothesis, which is the thing that we are making, is given that you're stuck with this human body at this point in time, we are claiming that the motions that we use are optimal for that particular human body. Why that human body is the way that is, I think that's a bigger question. It probably, there's lots of different evolutionary pressures and constraints, and it's not clear what all the things that you care about are in that broader context. And even for things like walking and running, obviously energy is not the only thing that you care about. In some situations you might care about speed. You always care about stability, right? So all these calculations that I showed are ignorant, if you will, of stability, right? So I'm assuming that you're able to track any trajectory, and the calculations are relatively ignorant of what happens if you perturb the person away from the trajectory. But for humans and animals, there is a constraint that you have to walk without falling down, because if you fall down, something that's chasing you is more likely to catch you, or you're more likely to injure yourself, and so on. But we believe that if you add that stability constraint, the motions that you get for energetically optimal strategies is not all that different. But I guess to answer your broader question, I think, I guess let me just say that we are just making the narrow assumption that we are optimal for this body, and how that body changes over time is another thing. And presumably the behavior changes in response to the body change.
Let's thank Manoj very much. Questions, feel free to come up and ask them after.